Welcome back. So last time we have studied about the electric field and electric field intensity due to a charge. Now let us find out what is electric field lines. Okay, so the next topic is electric field lines. Electric field lines. So in previous chapter or previous topic, what we have said, suppose a charge Q is here, and if I kept at the charge Q naught, then what will happen? So it will repel. And as we know that the Coulomb force act along the line joining the two charges, so this will be the direction of the force. Okay, if I keep this source R, this charge Q naught here, then the force will be along this direction. If I keep the source charge Q naught here, then the direction of the force will be along this direction. That means look at the direction of the force at each and every point. This is point number 1, point number 2, point number 3, and we found that the force is, the direction of the force are all different according to position of the test charge. So that means this is the direction of electric field here, this is the direction of electric field here, and this is the direction of electric field here. Okay, so the direction of the electric field also changes according to the position from the source charge. If I take the test charge Q naught here, the direction of force as well as electric field is along this direction. Okay. Again, if I take the source charge as negative, since it is positive, the test charge must always be positive. So that is why if I take a negative source charge, then look at the condition of this Q naught. So it will be plus, minus, the force is attractive. So the direction of electric field is also changed. The direction of electric field also changed. The force is along the line joining the two charges, so that is why the direction of electric field also changed. So these are the direction of electric field, which is towards a negative charge. Okay, so that means there must be, if I keep a charge here, if I keep a charge here, this particular charge, this is called the test charge, this charge tends to move in a particular direction. So it will move like this. If it is like this, it will move like this along the line joining. If this charge reach here, it will move like this. If the charge reach here, it will be like this. So that is why the path along which a unit positive test charge tends to move, that is what we call as electric field lines. So the definition of electric field line says it is the path along which a unit positive test charge tends to move. Unit positive test charge tends to move if it is free to do so. That means without any compulsion. If it is free to move, then in which direction or in which path it will move, that shows the direction of electric field lines. And it is an imaginary line, it is a concept, that means along which the electric charges, that is the test charge, tends to move. Okay, now if so, that means we will consider some of the properties. There must be some properties of these electric field lines. So let us discuss some of the properties of these electric field lines. So let us see some of the properties. Properties of electric field lines. First property says it always originates from the positive charge. It always originates from the positive charge and terminate at the negative charge. That means if it is a positive charge here, the electric field lines will be originating, that means away from the positive charge. If it is a negative charge, that means it will terminate, the field lines will terminate towards a negative charge. Okay, so the first point says it always originates from the positive charge and terminate at the negative charge. Second point says it originates or terminate. It originate or terminate at an angle right or normal to the surface of the charge. That means it always originate or terminate at an angle right. That means whenever it originates, the angle at which it originates or angle at which it terminates on the charge, it will be always 90 degree to the surface of that particular charge. Okay, suppose if I take a charge plane lamina, that means electric field will be originating from this charge like this. Okay, if it is a sphere, then it will be originating in the form of a spherical shape. Okay, so it will originate or terminate at an angle right to the surface of the charge. Okay, next, number 3. नंबर 3 में क्या बोला है? So the tangent drawn at any point on the field lines indicate the direction of electric field at that point. Look at this. It says that the tangent drawn at any point on the field lines indicate the direction of electric field at that point. Suppose your electric field is a curved line somewhere like this. So at this point, look at this, draw a tangent at this point. So this is the direction of electric field at this point. Draw a tangent somewhere here, so this will be the direction of electric field. The tangent drawn at any point indicates the direction of electric field at any point. Okay, so the electric field may be a straight line or it may be a curved line. Okay, so depending on the nature, you draw a tangent, and when you draw a tangent from that point, the tangent indicates the direction of electric field at that point. This is what it is mentioned here. Okay, next number is number 4. No two electric field lines intersect each other. One more topic is that no one more property, no two electric field lines intersect each other. That is what we have learned in class 10. No two magnetic field lines intersect each other. Similar case is here. That means no two electric field lines intersect each other. Let us see what happens if they intersect. Suppose this is electric field E1 and another field E2. Look at this. E1 and E2 are two electric fields. Then if suppose they intersect here, then at the point of intersection there will be two directions of electric field. There will be two directions of electric field from this single point, and at a single point there must be only one direction of electric field, and in such case there is two directions of electric field, which is not possible. Okay, so that is why no two electric field lines intersect each other. Why? Because at the point of intersection there will be two directions of electric field, which is not possible. Okay, now number 5. So these are 4 points. We can have another point, number 5. Now next point is electric field lines are continuous, so it means it will be continuing from the charge up to infinity, and if it is from infinity it will be up to the charge. Okay, so that is why it is always continuous. Suppose it is a charge plus q, electric field will be always from starting from the plus charge up to infinity. That means there is no break of this electric field line. There is no electric field here. It's not like this. Okay, so it will be electric field here, यहाँ पे है और यहाँ पे नहीं है, ऐसा नहीं है. Okay, so if it is electric field here, so it will be also there due to this charge. Okay, it is a continuous line or curve. Okay, next number 6. Number 5, number 6 we can write the closeness of electric field lines. Okay, let me tell you another name of electric field lines here. I remember the another name of electric field line. It is the electric lines of force. Electric field lines or electric lines of force. So the closeness of electric field lines indicate the strength of electric field at that point. Next topic is the closeness of electric field line. How close the electric fields are here. So look at this. So if you draw a field lines here, then you can have infinite number of field lines originating from the plus. So look at this. These are the electric field lines always originating from the plus charge. And look at this. These are the electric field lines. If you look at this region, the lines are very close. If you look at this region, the field lines are separating more. If you take here, the field lines are apart from each other. So that is why the closeness of electric field indicates the strength of electric field. Obviously, the electric field E1, E2, E3 will be different, and as it is moving away from the charge, so electric field is reduced. So we get a point that electric field, the closeness of electric field lines indicate the strength of electric field at that point. So that is why this is the point number 6. Okay. Next point is electric field lines contract. They contract. All the field lines contract. Not if it is a single, then it is not there. Isolated, it is not there. But if it is a system of charges, then this electric field line contract longitudinally, okay, and is responsible for the attraction of two unlike charges. Look at this, electric field lines contract longitudinally and it is responsible for the attraction of between two unlike charges. So this is the point number 8. Electric field lines exert lateral pressure on each other. They exert lateral pressure on each other and is responsible for repulsion between whom? Between two like charges. If like charges are there, they will repel. Why they will repel? Because of the exerting of the lateral pressure of electric field lines on each other. Okay, so these are some points. which you have to remember regarding the electric field lines or electric lines of force. Okay, now if you are asked to draw the electric field lines of certain system, so I will represent some of the electric field lines. Suppose we have a positive charge here, isolated positive charge. Electric field lines for isolated positive charge. So if it is positive, we will follow the rule, originate from the positive charge, 90 degree, the arrow indicates the direction of electric field. These are the arrows which tells the direction of electric field, and these are the arrows, and these arrows represent the direction of electric field for a positive charge, and it is away from the positive charge. Look at the arrows, direction of electric field. Okay, this is for whom? Isolated positive charge. This is the electric field lines. Draw the electric field lines due to an isolated positive charge. Or if we say Q greater than 0. Q greater than 0. Okay, then it is positive. Okay, Q greater than 0 is positive. Okay, next. Next comes for a negative charge, for an isolated negative charge. Now the second case is for an isolated negative charge. So if a negative charge is taken, so consider a negative charge here. So that is the electric field. I will draw this line, same line as we have drawn in the positive charge, the same lines, but only thing is that it is towards the electric field lines terminate at the negative charge, or this is Q less than. Now coming to third point of how to make the electric field lines due to a system of two charges. Say for example you have two charges, say positive and the negative. Positive, negative, that means unlike charge, a system of unlike charge. Then what should be the nature of electric field lines? So the nature of electric field lines will be look at this line, originating and terminating to the negative, originating from the positive, terminating at the negative, originating from the positive, terminating at the negative. Now you can draw the positive side here. Look at this line, originating from the positive and now terminating at the negative. Now this represents the electric field lines due to a system of two unlike charges. Okay, so a system of two unlike charges. A system of two unlike charges, that means you can say Q1, if you say Q1 and Q2, multiply with Q2, two charges, Q1, Q2 may be same or may be different, but it will differ in the nature. Okay, so Q1, Q2 greater than or negative less than 0. That means Q1, Q2 less than 0 means it is negative. So when you multiply plus and minus, you will be getting a negative value. So it is a system of two unlike charges. Okay. Now at last we will consider for like charges. Okay. Now coming to the system which is called a system of two like charges. A system of two like charges. Okay, two like charges, one condition is that it may be both positive, positive, or it may be both negative, negative. Okay, so here it may be both positives, or you can say Q1, Q2 plus Q or minus Q. Okay, and this is minus q, sorry, plus q, minus q, minus q. Okay, so that means q1, okay, q1, q2 greater than 0, positive, because plus plus positive, or you can say q1, q2 greater than 0. Okay, why? Because minus minus also positive. Okay, so it is repulsive, this also repulsive. Now look here, according to this, they exert or they contract longitudinally along the longitude, so that is why this is responsible for the attraction between the two charges. Now in this case, what you will find that they exert lateral pressure on each other, originate and move out. Okay, and now it originates and it will move out. Look at this, two lines. They exert lateral pressure on each other. Moving out, since these are plus sign, always positive. Moving out. Look at this. So this is the electric field lines due to a system of like charges. Similarly, you can draw here also. You can draw here also. You can draw here in the same manner as we have drawn here, but you can see the lines, same lines. The lines are same, but what is different? The arrows will be different. It is towards a negative charge. Okay, so it is towards a negative charge. Let's go to the next topic, which is called as electric dipole system. We have just now considered a system of unlike charges here, and we have drawn the electric field lines of unlike charges. Okay, so what happens if two unlike charges are there, and if the two unlike charges are of equal magnitude, then what it is called? So it is called electric dipole. Di means two poles having. Okay, so it consists of two equal and opposite charges, minus q plus q. Two equal and opposite charges, equal होना चाहिए, opposite nature होना चाहिए, separated by a certain distance. So we call this is the length of the dipole, and this is the center of the dipole. Okay, so we call this is the electric dipole, and the definition of electric dipole says it is a system of two equal and opposite charges separated by a certain distance. It is a system of equal and opposite charges separated by a certain distance, and this system is what we call as electric dipole. Okay, water molecules, HCl molecules, these are some of the examples which constitute electric dipole. Okay, so now if you know the electric dipole, then there must be a factor which represent the strength of electric dipole. Is dipole a strength? How to measure the strength of this electric dipole? And that is measured by one factor, one term, which is called as electric dipole moment, which is used to measure the electric field strength of this particular dipole. Then, how to measure the electric dipole moment? It is denoted by P vector. Okay, so it is the product of, it is the product of either of the magnitude of the two charges. It is a product of either of the magnitude of the two charges and length of the dipole. Okay, so then we write the magnitude of P vector equals to Q into 2A. Okay, Q into 2A. Okay, so here 2A is what we don't know, and that is why what happened, the vector, it is a vector quantity, then what should be the direction of the dipole moment? It is a vector quantity and it is from, the direction of the dipole moment is from minus Q2 plus Q charge. Now we got the direction of the dipole moment also. That means if it is minus Q, if it is plus Q, then the dipole moment is denoted by P. Okay, and this is the length 2A. Okay, so measurement of either of the two charges and the length of the dipole. Then what is the SI unit? SI unit of electric dipole moment is charge measured in terms of coulomb and distance measured in terms of meter. So coulomb meter is the unit of electric dipole moment. Okay, so these are some of the topics that we have studied today. So next time we will be back with another topic. Okay, thank you.